In this video, we are going to learn about how to count the number of significant digits or significant figures. So these two terms, they are basically the same thing. But for significant figures, we can abbreviate to something called sig fig. There you go. So we are going to use sig fig for the abbreviation to represent significant digit or significant figures. Now let's review. The structure of a number is basically a number is made of one or more digits. For example, if I have this number 105, in this case there is only one number, but there are 3 digits. Now, why is it important that we need to know about sig fig? First of all, the number of significant digits in a number of a measurement show the measurement precision. That is, a measurement number with more decimal places will be more precise. For example, if I have an instrument like a scale that has this measurement 1.0, where if I have another scale that go 1.00, this scale could worth $5,000, where this one can be worth for $20. However, precision is not the same thing as accuracy. Now, that is, you can still get very inaccurate measurement even when you are using a very precise instrument, because if you don't know how to use that specific instrument, you will use the instrument incorrectly. Therefore, you would have inaccurate measurement. Now let's get back to the focus of this video. That is, if we look at a number, how do we know if the number has a certain number of significant figures? First of all, there are only 3 situations when a digit in a measurement number is significant. And if that digit does not apply to one of the 3 rules below, it will not be significant. The first one is all non-zeros, basic 1, 2, 3, and so on, all the way to 9. All those digits are significant no matter what. And if you have a 0 that is in between a 2 non-zero, for example, if I have this right here, 1.01, this 0 is between the 2 non-zero, it is significant. Where if I have 1.00100, these 2 zeros right here are significant, but these 2 right here are not significant because they are not in between 2 non-zero. And here's the most important one of all, is that if you have a decimal number, that is the one have a dot like this, or the decimal point, then the first non-zero, so you're looking for the first non-zero, and all the digits, again I said all the digits after that non-zero right here are significant. Let's look at some example. First of all, this is not a decimal number, so therefore we look at the other 2. These 2 are significant, but these 2 zeros are not, because they are not in between 2 non-zero. So in this case, we only have 2 sig fig. Where in this case, we have a decimal number, and go back to rule number 3, again, the first non-zero and all the digits after that non-zero are significant. Here's my first non-zero, so all of them will be significant. In this case, 1, 2, 3, 4. So we have 4 sig fig. Let's try another one. We have 0.001. This is a decimal. Go back to rule number 3. Since this is our first non-zero, and it's the only digit, there's no digit after this one, so we know it's only 1. Then over here we have another decimal. Notice how this is our first non-zero, and all the zero and all the digit after that non-zero will become significant. So therefore, in this case, 1, 2, 3, 4. Isn't that easy? However, there are 2 exceptions. The first exception is that significant figures are only applied to measurement. That is, we use an instrument to get a number. And if a number is not measured, then we can ignore it. That means we don't care about the significant digit in that number. So we can assume that it has an infinite number of significant digits. That means all the digits in that number will always be significant. So again, the significant digits or figures only apply to numbers that are being measured, because every instrument has different precision. For example, in this case, my counting number. I have 5 apples. I count 5 apples. 1, 2, 3, 4, 5. I can prove that infinitely significant because I can prove every single time I count it. The same thing with 100 pennies or 100 tablets. Another exception is this. When we have a scientific notation number, remember in the Back-O day scientific notation, where we have the decimal part or the coefficient part times the exponent part. When we have a scientific notation, only the coefficient part determines the number of significant digits. So if we look at scientific notation, only look at this part. Let's do some example problem together. How about that? In this case, I have 1007.50 times 10 to the second grams of sodium chloride or NaCl. In this case, this is our coefficient. So this is a decimal number. We start counting from the first non-zero all the way to the end. So 1, 2, 3, 4, 5, 6. That gives us 6 significant digits. Then over here we have another decimal and a scientific notation. In this case, the first non-zero is right here. So it's 1, 2, 3, 4. Again, if we have a decimal number, the first non-zero and all the digits after the non-zero, that non-zero, are significant. So this is the first non-zero all the way to the end. So in this case, we have 4 significant digits. Now let's try some more examples. How about that? In this case, I have 10500. This is not a decimal number, so we have to go back to look at other rules. Here are the rules again. First of all, we know that this is significant because they are non-zero. But what about this 0? It is significant, it is between 2 non-zero. But this 2 0 are not significant because they does not follow any of the rules above. So we have 3 sig fig. Let's try another number. In this case, I have 0.001050. This is a decimal number, so we look at rule number 3. We look for that first non-zero and all the digits after the first non-zero are significant. This is our first non-zero and followed by all the digits after it. In this case, 1, 2, 3, 4, 5. So we have 5 sig fig. Then right here we have another number. This is not a decimal number. This is significant because they are non-zero. This 0 is significant because of rule number 2. 0 between 2 non-zero, and these are not significant because they didn't follow any of the rules above. So in this case, there are 3. And why am I only looking at this part? Because for scientific notation, we only look for the coefficient. Let's try another one. How many sig fig do we have? This is a decimal number. So the first non-zero is this one right here, and count all the way to the very end. 1, 2, 3, 4, 5. So we have 5 sig fig. And here we have 50 drops of H2O. Now drop, look at the word drop. In order to determine the number of drops, we have to count 1 drop at a time. So in this case, they have infinite number of significant figures because we can prove every single drop. Then we have 1.03 times 10 to 21 moles of water. This is a scientific notation, so we only look at the coefficient. So this is a decimal number starting from the first non-zero all the way to the end. 1, 2, 3. And that's all we have to do. And we have 11 shots of copper. The shot of copper are basically little pellets of copper. And we're going to count 1 shot or pellets at a time. So that way we can prove that it is always precise. So in this case, it has infinite sig fig. Then we have 500 grams of copper. So in this case, this is significant because it's a non-zero. And these 2 zeros are not significant because it doesn't apply to any of the rules above. And they are not between 2 non-zero. So in this case, we only have 1 sig fig. Then we have 0.01700 times 10 to the 23rd moles of copper. This is a coefficient of a scientific notation number, and this is the decimal number, and this is a decimal number. So we look for the first non-zero. This is not the first non-zero. This is not. And this is the first non-zero, and we count all the way to n. 1, 2, 3, 4. And then we have 4 sig fig. And that's it.